seen last class, formulation of quantum mechanics, that stationary states are very important and find energy eigenstates or the eigenstates of Hamiltonian. There, the time evolution.
Sir, your voice is not clear.
How is it now?
Yes, sir, fine.
So, I was last class in the formulation of quantum mechanics. I said that you have stationary states known, then the time evolution of any arbitrary state will be calculated. So it's important.
Sir, in between the volume is going low.
So disconnect the mic and reconnect it so it will work.
Hello?
Yes, sir, I think it's fine. Sir, your mic is muted now.
So leave the meeting and rejoin, sir, because you have disconnected the mic and connected. This will not come. Just leave the meeting and rejoin. It will work.
Hello? Is it work? Can you hear?
Not very good, sir. It's breaking in between.
Hello? Now?
Sir, can you speak again?
Hello? Hello?
Yes, I think it's fine.
Okay. So essentially, you can see the screen.
No, sir.
And okay, so now you can see.
Yes, sir.
Okay, so let us try to understand how to solve this equation in a few simple cases. Okay, so in all these calculations, I'm going to use coordinate basis. Okay, coordinate or what is called a position basis. So this is the basis in which I will do the calculations, and according to this basis, all the states are written as functions of x. An x operator operating on some function psi of x is simply x multiplied by psi of x, and p operator acting on psi of x will be equal to h bar divided by I into d by dx acting on psi of x. So the moment I make a choice coordinate or position basis, these two operators are defined in this fashion. These are the correspondence. Now, once we know this, then of course I will use a one dimension. Okay, so that means my independent variable is just x. Okay, that is one dimension. So, one of the first problem that I would like to solve is something called particle in a one-dimensional box. Okay. So let us write down the potential for this. The potential for this is given by V of x is equal to 0 if modulus of x is less than a, and it is infinity if modulus of x is greater than a. What does that mean? This means if you imagine that you have an x and y axis like this, so there is something called minus a here and plus a here, and between minus a and plus a, this it is 0, and at plus a and beyond plus a and beyond minus a on this side. Okay, so in this region the potential is infinity. In this region also the potential is infinity. Only in this region the potential is 0. That means it is a kind of a free particle in this region. So this is x is equal to 0. Okay, so this is the kind of a box that we have, and we are interested in finding out a potential for this. Now, in all these problems, what we do is we consider regions in which potential is different. Okay, for example, this region, that is x less than minus a, this region I will call it as region 1, and this one I will call it as, that is minus a less than x less than a. This region I will call it as region 2, and x greater than or equal to a, this region I will call it as region 3. Okay. Now, since the potential is infinite, we can immediately understand that there won't be any particle in that case. So psi 1 of x is 0. So is the case with psi 3 of x. Psi 3 of x is also equal to 0. So this one we can immediately write down from the fact that the potential is infinity in those regions. Now psi 2, okay, so let us say that let E be the energy of the particle. Okay, so we have to solve this problem. And what will be your Hamiltonian? Because inside that potential, Hamiltonian is p square by 2m, which is given by, this implies the Hamiltonian operator is equal to minus h bar square by 2m into d square by dx square. So this is the Hamiltonian operator. So the eigenvalue equation, that is h psi is equal to E psi. Okay, so this equation can be now recast as a differential equation, which is minus h bar square by 2m d square psi by dx square is equal to E psi. So it is customary that you write this differential equation in this fashion: d square psi by dx square plus some k square psi is equal to 0, where this k square is twice me by h bar square. So if I call this as k square, then this equation will be having a form like this. Now, a second order differential equation like this can be solved. Okay. So there are many ways in which you can write down the solution. If you write down an auxiliary equation for this, then the roots of the auxiliary equation will be plus minus ik. So you can write down the solution psi of x as some a e power ikx plus b e power minus ikx, because e power ikx and e power minus ikx are solutions of this differential equation. Or you could write equivalently, you could have written psi of x is equal to some a prime cos kx plus b prime sin kx, and a prime and b prime can be related to a and b. Okay, so this is another way in which you can write. Or equivalently, you can write psi of x is equal to some a sin kx plus some delta. This is another way to write. See, this is a second order differential equation, so there should be two constants, a and b, and here a prime and b prime, and here you have a and delta. Okay, so with two constants, you can write it either like this or like this or like this. Now in problems, which of this form you should use, okay, that depends on the context. Actually, mathematically, you can use any one of these, but it will be simpler if you choose some form. Okay. Now, in this particular case, your energy is so the potential walls are at infinity. So energy is less than infinity. Anyway, it's a finite energy. So the particle is bounded. So whenever you have bounded kind of a wave function, then it is always better to consider this kind of thing. If you consider this, then you have to do a little more work to come to this, but it is always better to consider this. So my psi 2 of x, now I will simply write this as a cos kx plus b sin kx. Okay. Now I have to, so there are two ways of solving it from here. One is a kind of a brute force. Okay, so that means I am going to write down that psi 1 of minus a is equal to psi 2 of minus a. This is the boundary condition. Or this is equal to 0 anyway. So that is equal to 0 because psi 1 is 0. And psi 2 of plus a is equal to psi 3 of plus a, which is equal to 0. So psi 2 of minus a is 0 and psi 2 of plus a is 0. These boundary conditions you put in, and then you get some equations, solve those equations to find out the allowed values of k. So what is the final aim here? Aim is to find allowed values. Okay, so this is what we will do, but let me try to do it slightly intelligently. Now note that there is some symmetry in the problem. Okay, so since b is equal to 0 between minus a and plus a, so note that v, which is anyway 0, is invariant under x going to minus x transformation. That means v is an even function of x. Of course, it is 0 here, but there is this symmetry, transformation. Okay, that means there is some parity symmetry. So whenever this happens, okay, then whenever this happens, you can say that eigenfunctions of H have definite parity. What does that mean? That means either they are even parity or odd parity. Okay, that is even or odd. Okay, so now this function I cannot have this function because this function does not have parity. So suppose I say that I want to have even parity wave function. Okay, so let's say that I ask for even parity wave function. Even parity. So if I demand even parity, then this psi2 of x is equal to psi2 of x is equal to simply a cos kx, because cos kx is the only function that has even parity, but this is an even function. Okay, then you can confine to just 0 less than x less than a, and get wave function as psi of minus x for minus a less than x less than 0. So if you can find psi of x, then in the other region, that means here I am going to now concentrate only in this region. So in this region alone. So if you know that this is psi of x, then in this region it is psi of minus x. That much is. So if it is even function, it is same function that is here. If it is odd, then this is minus of that. So like that. So if you have even parity, then you have a cos kx. Now the boundary condition that I have to use is simply the boundary condition at A. Okay, so that means the only boundary condition that I need is psi2 of A is equal to A cos Ka, that is equal to 0. Okay, so that is I am only looking at the boundary condition at this particular boundary. So A cannot be 0, because if A is 0, then we will get trivial solution. It implies cos Ka is equal to 0. So that means your Ka is equal to n pi by 2, where n is equal to odd numbers 1, 3, 5, etc. Correct? So this is what will be your condition on A. Ka is equal to n pi by 2. Okay. So now we can write down, this implies K is equal to n pi by 2a. K is equal to n pi by 2a. And the solution psi2 of x is equal to a cos n pi by 2a into x. Okay, n pi by 2a into x. Of course, wherever you write n, you have to write this n is equal to odd numbers. Okay, now let us look for odd parity solutions. So if you ask what is odd parity solutions, so for odd parity, your psi2 of x will be equal to some b sine kx, because sine is the only function that has a odd, it's an odd function. So now what happens? I have to again demand that psi2 of A is equal to 0, which implies B sin Ka is equal to 0. Okay. So that implies B cannot be equal to 0, which implies that your Ka is equal to n pi. Ka is equal to n pi. Now this is, so this implies K is equal to n pi by A. K is equal to n pi, so K is equal to n pi by A. Now look at this one. If you have, so K is equal to n pi by A. Okay. Now what you will see is that, and your wave function, that is psi2 of x, is equal to B sin n pi by A into x, n pi by A into x. In this case, n can be any integer. So n is equal to 1, 2, 3, etc. Okay. But remember, if I put any even integer in this expression, I will get this. Okay. Now let us try to just look at what happens in the case of, so now what is it that we have? We have psi2 of x will be equal to cos n pi by 2a into x. Of course, there is some constant a, and n is equal to 1, 3, etc. And here you have some b sin n pi by a into x. Now, if n is equal to 1, this is what is odd, this is what is dominant. So for the remaining things, if I want to do like this, 2, 6, 4, 6 like this, okay, then I must divide this by 2, because if it is 2, 2 by 2 is 1, 4 by 2 is 2, like that. So if I put 2 here, then I can say that this n corresponds to, then what happens, this argument and this argument will become same. So these are the wave functions. Okay, so this a and b, of course, we have to determine. Now we can say in both the cases, the energy is given by h bar square k square by twice m. So that is equal to h bar square by twice m into what is k. So if I take, in this case, if I want n is equal to 2, 4, 6 like that, then this k will be equal to n pi by 2a. So same k in the previous case and this case. For even, it will be like, so that means this is equal to n square pi square by 4a square. So the energy eigenvalues of this one are given by n square pi square h bar square by 8ma square, and these are the energy eigenvalues. Okay, so these are the energy eigenvalues. Now we have to normalize the states. So normalize the wave function. Okay, so it will be either cos square or sin square. Suppose even parity wave function will be a square integral minus a to plus a cos square n pi by 2a dx dx. So that is equal to a square integral minus a to a. So I would write this as 1. So there is a half 1 plus cos n pi by a into x dx. So that is a square by 2. So I want this to be equal to 1, right? So this is equal to 1. That implies, so this is equal to 1. So a square by 2, and I have two terms here, minus a to a dx. That's the first term. And second term is cos n pi by a x dx. So that if I integrate, that will become a by n pi into sine n pi by a into h from minus a to plus a. That's equal to 1. So you know that sine n pi is always 0. So this term will become 0. So you have, this implies a square by 2, and this is a minus of minus a is 2a by, so you have 2a is equal to 1. It implies your a is equal to 1 over root a. Now you can see that you will get the same thing even if you have sine square, because it is instead of 1 plus cos 2 cos n pi by, you have 1 minus cos n pi by. So this term anyway will not contribute. So you have, including this normalization. So if you say that you have h psi n is equal to E n psi n, this equation is solved for this system. Okay, and the solution is that your En, the energy eigenvalue, n square h bar square pi square divided by 8m a square, okay, and your psi n, right, is equal to 1 over square root of a. Okay, yeah. So this is into, you have cos n pi by 2a x if n is odd, and sine n pi by 2a into x if n is even. Okay, so this is the solution of this equation, of this problem.
Sir?
Yes.
Sir, here how to take minus a to a? Isn't it 0 to a? Cos square normalizing condition.
No,
Because
minus is the full range you have to take. No? The box is from minus a to plus a.
yes, sir. But here you have taken the only the even part wave function.
No, see, that is only to get boundary conditions. I have chosen that. See, actually, what you have to do is you have to take both a cos kx plus b sin kx. Okay.
Yes.
So either you take this and apply boundary conditions and do this. That is what I called as brute force. But I am trying to not to do that. I'm actually exploiting the symmetry that is there in the system, and then I'm taking for even parity functions only cos kx, odd parity functions only sin kx. When I do this, in the boundary condition, I don't have to put boundary condition at x equal to minus a. That is the only thing. After that, your function will be belonging to the entire interval. Okay. So this is the the simple way in which you can solve this function. Now Many times in textbooks, what they will do is they will try to solve particle in a box in a different domain. For example, people say that you can say that your V of x, let's say, is defined as 0 between 0 between x and a and infinity otherwise. So you can define like this. Yes, that means you have this goes to infinity here, and this is all infinity here. This is all infinity here. This is 0, and this is here. Okay. So if you do this one, then you will get. I will leave it as an exercise. This is a simple exercise. So you can get this as En is equal to n square h bar square pi square divided by 2ma square. Okay. And then your psi n of x will be equal to square root of 2 by a into sine n pi by a into x. Okay. Now notice that here the box length. Okay, so box length is a, whereas in the above case box length is 2 times a. Okay, so here you can see box length here is 2 times a. Okay, so in the energy eigenvalues, instead of a, if you take 2 times a, then energy eigenvalue will be same as the above one, because it will be 4a square. Instead of a, you put 2a, it will be 4a square. Then the energy eigenvalue will be same. Now this one is, or in other words, if you consider this box, okay, suppose you take this box size as a, that means it is like minus a by 2 less than x less than a by 2. So suppose you take this instead of a, if you take box size a, then this becomes, here you have to put a to be a by 2, then you will get the same energy value. Okay, so the energy eigenvalues will depend on box size, whatever from whichever between whatever coordinate this box is, it is not important. Now the correspondence between so here also in this wave function also you will get cos n pi by a, because wherever a is there you put a by 2, so this becomes cos n pi by a, this becomes sin n pi by a. And this in the normalization constant where a is there, you put a by 2, you get root 2 by a. Okay, but then here you have cos and sin, whereas here you have only sin. So how do we understand this? See, what you can do is that suppose you make a transformation. Okay, so make a change of variable. So what is the change of variable that I will do? I will say x. So x is going to be equal to x minus a by 2. That is, x goes to x minus a by 2. So that, so this x minus a by 2 is my new variable x tilde, let's say. So what happens if x is equal to 0? Now x tilde is minus a by 2. And if x is equal to a, x tilde is plus a by 2. So now what happens? This 0 to a is now shifted to minus a by 2 plus a by 2 in terms of this new variable x tilde. So now you ask, what is this psi n of x tilde? Psi n of x tilde. So that will be equal to, so wherever x is there, you have to put x tilde plus a by 2, right? So that is root 2 by a into sine n pi by a into x tilde plus a by 2. So that is equal to root 2 by a sine n pi by a into x tilde plus n pi by 2 plus n pi by 2. Now you look at, for example, now you ask what is psi 1 of x. Psi 1 of x tilde. Psi 1 of x tilde is root 2 by a into sine pi by a into x tilde plus pi by 2. So sine pi by 2 plus is basically root 2 by a into cos pi by a into x tilde. So you can see in terms of this x tilde, it is same as, okay, so for this box, okay, so let me write it here. For box minus a by 2 less than x less than a by 2, in the previous problem itself, we will have En is equal to n square h bar square pi square by 2ma square, and your psi n of x is equal to root 2 by a into cos n pi by a into x, n is equal to 1, 3, etc., or sine n pi by a into x if n is equal to 2, 4, etc. So this is the result for the box minus a by 2 to plus a by 2 according to what we have shown earlier. Now I am trying to say that you put n is equal to 1 here, it will be cos pi by a into x, and that is what we are getting here. So so if you solve the problem in that fashion, you just make a transformation that x tilde as x minus a by 2, you will get that solution. Okay, so the conclusion that we are drawing is the solution or the wave function for stationary states of a box minus a by 2 to a by 2 can be obtained from the set of wave functions of the box 0 comma a by a change of variable x going to x minus a by 2. So in this transformation, this 0 to a will go to minus a by 2 to plus a by 2, and that transformation will actually make a correspondence between these functions. So it is not necessary that we should solve these problems again and again. Once you solve it, then you have to adjust your box in such a way by making appropriate transformations, and you can see that a similar problem can be solved.
So it is basically like we are shifting the origin. That's
Yes.
it, no, sir. The box's
Yes.
origin, and
Correct.
it is like operating some translation operator, like psi of x plus a.
Yeah.
I think, yeah.
Okay. So this is one problem, and we can actually think of, now that we have made some this thing with correspondence between this. Now let us consider another problem. Okay, so let's look at a second problem. Problem 2. So this problem is with respect to a potential like this. The v of x is 0, or let's say it's infinity. If x is less than or equal to 0, and it is 0 if 0 is less than x less than a, and it is some kind of a v naught if x is greater than or equal to e. Okay. That means the difference between previous problem and this problem is that it has infinity on one side. So if you plot this one, the potential, so this is infinity on this side. This is all infinity, and up to a it is 0, and on the other side it's not infinity, but it is some kind of finite value. So this is, so on one side we have a finite value. Okay, so now what happens? This problem is quite interesting because this is like a cartoon kind of a potential to many realistic potentials. Okay, so potentials like van der Waals potential or Coulomb potential with centrifugal barrier, all of them will have this kind of a shape. Okay, so typical interaction potential, typical interaction potential as a shape which you can see that it will be repulsive at small distances, and then it will be attractive, and at very large distances it becomes zero. Okay, so this is, suppose it will be some kind of a V of R versus R. So this is a typical, so this potential is in some sense, this is kind of uh, a simplified version of this kind of, because the shape looks like this. Okay, so it is kind of a uh, toy model of such potential. So solving solving eigenstates of this kind of a potential will throw some light on the general behavior of the interactions itself. Okay, so here we'll try to first look for bound states. Okay, bound states. In the previous problem, all states are bound states because your potential is infinity. But here, right hand side, the potential is not infinity. So the necessary condition. So necessary condition for existence of a bound state for a particle with energy E in this potential well is E should be less than V naught. If V is greater than V naught, then it will not be a bound state. This is a necessary condition. Okay. I'm saying necessary because it may not be sufficient. That means not that every E less than V naught will be a bound state. Okay. So this is some kind of a necessary condition. Definitely, it is a necessary condition. So let us look for bound states. That means I am assuming that E is less than V naught. Just give me a minute. Okay, is it visible now? Screen.
Yes, sir.
So, this is the necessary condition. So E has to be less than. So let us look for solutions like this. So now in this region, so let us look at. Let us call this as region 2 and this as region 3, and then this is basically region 1. And we don't have to do this calculation again. So psi1 of 0, psi1 of x is equal to 0 for x less than or equal to 0 because this is infinity. And your psi2 of x can be written as a cos kx plus b sin kx because the potential is 0 in that region. So the differential equation will be exactly like in the previous case. Okay, so what is k here? K square is equal to twice m e by h bar square. Now, the third region is what is important. Okay, so let us write down in the third region. So in region 3, we have v of x is equal to v naught for all x greater than or equal to a. So your equation, Schrodinger equation will be minus h bar square by 2m d square psi by dx square plus v naught into psi is equal to e. So this gives you that d square psi by dx square, okay, plus twice m by h bar square into E minus V naught is equal to 0. Now, since E is less than V naught, this implies E minus V naught is negative. Okay, so we write this as d square psi dx square plus some alpha square into psi is equal to 0, where not plus but minus, where my alpha square is equal to twice m into V naught minus E. I pull out a minus sign and then write this in this fashion. Alpha square is equal to this. Now, because this is an equation like this, solutions for this equation will be e to the power alpha x and e to the power minus alpha x. So these are the solutions. Okay. Now, even though general solution is so for example, now I can say this is equal to some c into e to the power alpha x plus b into e to the power minus alpha x in general. But we require the wave function to go to 0 as x goes to infinity. Okay, otherwise, if this e power alpha x term is there, it will go to infinity. So that is not a valid wave function. So since psi 3 of x has to go to 0 as x goes to infinity, so we have to set c is equal to 0. So because of this boundary condition, my psi 3 of x now simply becomes d into e to the power minus alpha x. Okay, so this is the situation. Now we can ask what are the boundary conditions that we have to consider. So this is x equal to 0 and this is x equal to a. So that means your psi 2 at 0 should be 0 and psi 2 at a should be equal to psi 3 at a. And of course, when this wave function is non-zero on both sides, the derivative of this should also be equal to derivative of that, whenever, of course, the potential is finite. Okay, so these boundary conditions, if you put in, so remember this is your psi 2 of x. Okay, so now if you say that your psi 2 of x, psi 2 of 0 has to be equal to 0, that implies you cannot have this cos kx. Okay, so this cannot be there. That implies a is equal to 0. So what is the psi 2 of x that we have right now is psi 2 of x is equal to b sine kx, and psi 3 of x is equal to d into e to the minus alpha x. So now between these two functions, we should be able to implement these two boundary conditions. That is this boundary condition and this boundary condition. So psi 2 at x equal to a is equal to psi 3 at x equal to a. So that means b sine ka is equal to d into e to the minus alpha a. Okay. Then there's another condition, that is psi 2 prime at x equal to a is psi 3 prime at x equal to a. So that tells you you have b k cos ka is equal to minus d alpha e to the minus alpha a. Okay, now you have these two conditions, and what is the aim? Aim is to get allowed values of k, allowed values of k. So we can say that so I take this equation in the numerator and this equation in the denominator, divide this by this, then I will have k cot ka is equal to minus alpha. K cot ka is equal to minus alpha. Because d to the minus alpha a sin ka, all that, I mean, this will become cot ka. Like, okay, so let us try to define some things like this. So define xi is equal to ka and some eta is equal to alpha a. So you multiply a here and a here. So then you can write down with this definition, psi cot xi is equal to minus. Okay, so we have to solve this equation to get allowed values of xi, and eta and xi are not independent. Remember that. So this equation is basically a transcendental equation. Transcendental equation, and this equation requires you have to solve it either numerically. Okay, so you can solve it numerically, or the other way of solving it is graphically. Okay, so let me just illustrate how do we do it graphically. Now remember, suppose what is your eta? Eta is equal to alpha a, right? So eta is equal to alpha a, or this implies eta square is equal to alpha, eta square is equal to alpha square a square. But what is alpha square? So if you go back and then look at what is alpha square, twice m by h bar square v naught minus e. That is equal to twice m by h bar square into v naught minus e into a square. But what is twice m e by h bar square? Okay, so also note xi square is equal to twice m by h bar square into e into a square. Okay, so that means now you can write this one as twice m v naught into a square divided by h bar square minus xi square. What is this equal to? Eta square. So from this we can write this xi square plus eta square. Xi square plus eta square is equal to twice m v naught a square by h bar square. Okay, that means this equation implies in eta xi plane, the above equation is a circle. The circle with radius, the radius square root of twice m v naught a square divided by h bar. So this is a circle equation in eta xi plane. Okay, so that means what? You are actually having an eta xi plane Okay, so you are actually trying to. So now what I'm going to do here is, you see, this is basically xi. So the equation to be solved is, I will put it like this: minus xi cot xi is equal to eta. So graphical solution works like this. Graphical solution. So what you have to do is plot left hand side as a function of xi, and plot right hand side as a function of xi. Okay. Now solution or solutions of this transcendental equation are points of intersection of these two graphs. That is, LHS and RHS, if they intersect at some point, that will be a solution of this equation. Okay. Now, what is the right hand side as a function of xi? Because eta and xi are related according to this equation. So that when you plot right hand side, it will be eta xi plane. That will be a circle of the radius given by square root of twice m v naught a square by h bar square. So that is something which we understand. Now left hand side you have to plot. So let us try to understand how to plot this left hand side. So first let us try to plot cot xi. Okay, so let's plot cot xi. So let's say cot xi is equal to cos xi by sin xi. Okay, so what will be cos xi? Cos xi at xi equal to 0, if you take, this will go to infinity, right? Sin 0 is 0, cos 0 is 1, so it will be infinity. So at so let us say this is 0 and this is pi by 2, and this is pi, let's say. So you start from 0, and at pi by 2, cos pi by 2 is 0, sin pi by 2 1, it will become 0, and again at pi it will go to minus infinity. So the cot will have a graph like this. Okay? It will have a graph like this. Okay, so let me just plot one, but then I want to plot minus cot xi. So minus cot xi, what does that will be? This will become, so minus cot xi is something like this. You start from here, and then this minus infinity will be this. So this is minus cot xi. Okay. Now let's say we have to, and then what? You have something called xi, right? So let's say xi is a straight line like this. This is xi. Okay. Now, if you multiply this minus cot xi into cot xi, okay, so minus cot xi. See, cot xi is a dominating factor because that is what will have what is called all the all the powers of xi basically. So if you are trying to plot let's say minus xi cot xi, minus xi cot xi will not be very different from minus cot xi as far as at least first quadrant is concerned. So let's say this is 0 and this is pi by 2 and this is pi. So we'll start from infinity like this and it will cross this at pi by 2 and then it will go off to minus infinity and this stuff. So this will be your minus xi cot. This is the left hand side. This is the left hand side of our equation. Now what happens? I have to plot right hand side, and right hand side is a circle. Okay, so I'm only interested in a part of the circle like this. Let's say that you have a circle like this is a part of the circle. This is your right hand side. So this point where this intersection is there, okay, so this point is allowed value of xi or k, because xi is equal to k times a. Allowed value of xi or k. Okay, so this is how we obtain this graphically. But now you notice one thing here that, for example, you notice that if the circle is something like this, okay, if circle is something like this, okay, so if this is your RHS, then what does it mean? No intersection. That means no allowed values of k. What does that mean? That means there is no bound state. So you can see that for this intersection to happen, the radius has to be at least greater than pi by 2. Okay, so that means you can see that uh, bound state exists if the radius of the circle in eta xi plane is greater than pi by 2 or greater than or equal to pi by 2. Okay, so that means we have this relation. What is the radius? The radius is square root of twice m v naught into a square by h bar square. This has to, so the minimum value of radius for which bound state exists, this is equal to pi by 2. Less than pi by 2, no bound state exists. Correct? So that means, suppose if I square on both sides, okay, so I will have twice m v naught a square by h bar square is equal to pi square by 4. Or in other words, v naught should be equal to h bar square pi square divided by 8m a square. Okay, so v naught has to be this much or greater than this much. Okay, so that means this is the sufficient condition, not so for existence of bound states, for existence of bound states with box size A for a particle of mass m. Okay, for existence of bound particle mass m, the necessary condition is that the energy E has to be less than V naught, but is not sufficient. Okay. In addition, if V naught is greater than h bar square pi square by 8 ma square, then bound state exists. So what does that mean? That means this is something like this. Suppose if you have a V naught which is like this, okay, small V naught. Okay, you may have an energy which is less than this. Okay, so in this case, bound state may not exist. Bound state may not exist. There is some threshold value of this V naught. Okay, so V naught should be greater than a threshold value. Only then the bound state exists. And that threshold value is given by h bar square pi square by 8 m. Threshold value depends on the size of the box as well as mass of the particle. So if it is more than that, then the bound state exists. Okay, and then what is the bound state? You have to determine by looking at the intersection points of this. So this is an important point, and usually in all problems where we have this centrifugal barrier, this is important. That's not every attractive interaction or whatever V naught is basically admits a bound state. It should have some sufficient depth to admit a bound state. Okay. So this is one just an extension of that one. That is one side we are trying to take this one. One side we are trying to take this finite case, and other side is infinite. Okay, so now you can think of asking a question that I will try to. We will try to look at a problem where both sides we will make a finite value. So that means we are now going to ask the following question: that we have, let's say this is our problem 3. So now we say that we have the potential is something is equal to V naught if x is less than 0, or less than or equal to 0, or x is greater than or equal to 0 if 0 less than x. That means we have something like this. We have so here also it is V naught, and here also it is V naught. Okay, so now also we can suppose, let's say that we look for bound states. So what is the necessary condition? Necessary condition seems to be this is x equal to 0 and this is x equal to 0. The necessary condition is that E has to be less than V naught. E has to be less than V naught. Let us consider that situation. Now what happens? Let's look at this as region 1 and look at this as region 2 and call this as region. Okay. Now what happens? In region 1, we are going to have some kind of A into e to the power alpha x, because x is negative here. It will go to negative infinity. Only this function will go to 0 as x goes to minus infinity. So what is alpha square? Alpha square is twice m by h bar square v naught minus. That is the first region. A second region in the second region, we are going to have sorry, I think I have to put some other. So let me call this as A1. So this is A2 cos kx plus B2 sin kx. So this is a bound state. So and what is k square? K square is equal to twice m e by h bar. And in psi 3 of x, we can have A3 e to the power minus alpha. Because as x goes to infinity, this has to go to 0. Now you have finite boundaries at both locations. So the kind of boundary conditions that you will be putting here is something like psi 1 at 0 is psi 2 at 0, and psi 1 prime at 0 is psi 2 prime at 0. These are two boundary conditions at the boundary x equal to 0, and you have at x equal to a, psi 2 of a is equal to psi 3 of a, and psi 2 prime of a is equal to psi 3 prime. Okay. Now we can see what happens if I apply these boundary conditions. The first one is I put x equal to 0, so a1 is equal to 8. So this is the condition that I will get from here. The second condition is that is from here I will get A1 alpha is equal to B2. Okay, so I will get this one from this condition. So after I applied these two boundary conditions, let me rewrite that equation. So psi1 of x is equal to A1 e power alpha x and psi2 of x is equal to A1. Okay, A2 is also A1 and cos kx plus B2 is basically A1 alpha by k. So I will write this as alpha by k into sin k. Correct? That is what we have from here. So then, of course, psi3 of x I have not used it so far. So psi3 of x is equal to some a3 into e to the minus alpha. Now let us look at this set of boundary conditions between psi2 and psi3. So you have a1 cos k times a1 cos ka plus alpha by k sin ka equal to a3 into e to the minus alpha a. This is this boundary condition. Then the derivatives. Okay, so the derivatives will be a1 k into sin ka so I think there is sin ka is, I think this is minus, right? So minus sin ka plus alpha by k, I will get a k out. So that k I have anyway written it here. So that is alpha by k into cos k is equal to, we'll have minus a3 alpha into e to the minus alpha. Fine. Okay. Now,
Wait.
yes. Hello.
No,
Yes. Any question?
sir. The fourth part, the psi 2 prime a that we have calculated, isn't it a2k instead of a1k?
But I have already shown here a1 is same as a2.
Oh, okay, okay.
So I have substituted for a2 and b2 from this. Okay. So now what I can do is, okay, so let us try to write it in the following fashion. Now I have only these two equations. So let me say that I will write a1 cos ka. Suppose if I pull that out, then I have 1 plus alpha by k into tan ka is equal to a3 into e to the minus alpha a. And here also, let me say I will pull out A1 cos Ka. Okay, so A1 cos Ka. That means I will take this K inside. Okay, so that is equal to minus K tan Ka plus alpha is equal to minus A3 e to the minus alpha A. Okay, so now you can see that. So let me say that. Okay, there is an alpha here. Now I pull out alpha also. Okay, so let's say I put that 1 here and K by alpha here and then alpha here. Then this alpha can be cancelled with this alpha. Okay. So now you can see that if I write down, so suppose if I take a ratio of this, okay, that is let us say that 1 plus alpha by K tan Ka divided by 1 minus K by alpha tan Ka is equal to minus 1, because this is A1 cos Ka will cancel, A3 to the minus alpha A will cancel, so right hand side will be simply minus 1. So this is, so what is this one? This condition should give us allowed values of K. Allowed values of K. So that is equal to 1 plus alpha by K tan Ka is equal to minus 1 plus K by alpha tan Ka. Okay. Or in other words, I can take this will be tan Ka into alpha by K minus K by alpha equal to minus 2. Okay. So this is basically, you have an equation like this: tan Ka is equal to minus 2K alpha divided by alpha square minus K square. Or I can write this as tan Ka is equal to 2K alpha divided by K square minus alpha square. So this is another transcendental equation which you have to solve in order to obtain the allowed values of K. Now you can see that this equation has, so let us look at left hand side, there is no problem. Let's look at the right hand. So you know what is K square. So K square is twice m E by h bar square. And what is that? Alpha square is twice m V naught minus V. And so you can see that so one way to look at this is something like this. If you say that you have, so let's look at some trigonometry. Suppose, let's say that you have some triangle like this. Let's say this is your Ka. Then what you can say about this is that it is opposite side. No, this is like 2Ka, take 2K alpha, and this is like k square minus alpha. What will this be equal to? K square minus alpha square whole square plus 4 k square alpha square. So which will be equal to k square plus alpha square, isn't it? Whole square. So this will be equal to k square plus alpha square. Okay. Then from this I can write down that sine Ka is equal to 2k alpha divided by k square plus alpha square. Okay. Now, what is k square plus alpha square? So k square plus alpha square is equal to twice m e by h bar square plus twice m v minus twice m v by h bar square minus twice m e by h bar square. So this will cancel. So k square plus alpha square is simply twice m v by h bar square. So this is something which does not depend on energy, or this is some constant, so which I will call it as, if you want, I will call it as some alpha naught square. So we have this sine Ka is equal to 2k alpha by some alpha naught square. This is anyway constant, it does not depend. But alpha, this alpha will have this k. So this is equal to something like I have. Okay, so this is the transcendental equation which you have to solve. Okay, or you can write formally that Ka is equal to sine inverse of 2k alpha by alpha naught square. Of course, you are not going to get anything more than what you get from this. Now, k times alpha is something like twice m by h bar square into square root of e into v minus into v minus. Or in other words, you can write it like this. So k times alpha is equal to k times square root of alpha naught square minus k square. Okay, so you have right hand side is k into square root of some constant minus k square. And of course, there is a 2 here, 2k alpha by alpha naught square by alpha naught. So you have to see how you can plot this one. This you can do it even at this level. So the right hand side and left hand side has to be plotted. RHS has to be plotted as a function of k versus k or ka, and this versus k or ka to find the allowed values of. But now you notice one thing, that whatever is the graph, okay, so if you just think of tan Ka, so tan Ka will be something like so tan 0 is 0 and tan pi by 2 will be infinity, right? So tan Ka is tan xi is sin xi by cos. So that is this is 0. So this is something like this. It will go from infinity, it will go to 0, then it will go like this. Will be your tan psi. Now, whatever is the graph of the right hand side, whatever is the graph, it will always intersect this one. Correct? So RHS as a function of psi, which is equal to Ka, intersects tan psi for all V naught. There is no threshold V naught. That means the bound state exists for E less than bound state exists for E less than V naught. So there is no threshold condition. So at least one bound state, I must say that at least one bound state exists for E less than V naught. There is no threshold condition here. So this is what we understand from this problem. Now, one way to look at this is kind of a physical motivation, something like this. So the question that we are asking is that if you have a well like this, so this goes to infinity here, and this is V naught. Okay. So the bound state exists for V greater than h bar square pi square by 8 minus. Whereas if you have a well like this, where this is V naught and this is also V naught, okay, it's the same 0 to A and 0 to A. That is what we have considered here. Okay, then you can see that bound state at least one exists for all V naught. Okay, so that is what happens for this potential. Now, the way to understand this is that your wave function can actually proceed in both directions in this case. It means its tails can go in both the directions. So you can have smaller and smaller energies such that the wave function can tail into both the regions. Whereas here, the wave function can tail into this region, but the wave function has to go to 0 at this region. So this cannot tail into this region. And because of that, for existence of a bound state, you require some threshold value, because there is a repulsion, there is a kind of a reflection from this wall, strong reflection. Unless there is sufficient amount of strength in this wall, the bound state does not exist. Whereas here, there is no strong reflection from any side. Wave function can actually propagate, extend into both the directions because of the finite potential well. You see that for whatever small v naught, at least one bound state exists. But you can ask a question, what will happen to if you want to exist two bound states? Then there will be some threshold value. But at least one bound state is guaranteed for a potential well where the boundaries on both sides is finite. So this is what is the way in which we. But in this particular case, of course, I have only concentrated on bound state problems. But we can also talk about scattering states. That means for which the energy is more than V naught. Okay, so that is an interesting problem. Also, of course, in finite potential well, you have no scattering states, but For other two cases, where one side finite and both sides finite potential wells, one can talk about scattering states. And the stationary states will be both bound states and scattering states. You have to consider both of them. That is what leads to the complete set of eigenstates of the Hamiltonian. Okay, so scattering states correspond to kind of a free particle states. Bound state wave function will be corresponding to this kind of a boundary condition sum. So, yeah, I will stop here if you have some questions.
So,
Hello, sir.
Yes.
you showed that. So for the sir, can you open the video? So for the first example, you showed that at the beginning you showed that there is a symmetry in the whole situation that you gave, the whole case. So using that symmetry, so there's a initial symmetry was in the potential V that was given to us, and using that symmetry, we created a symmetry in the H Hamiltonian. So, sir, is it true for any system that if the symmetry is existing inside the potential, the Hamiltonian will similarly get the symmetry, and we can use this parity thing?
Yeah, because so the Hamiltonian is, I am talking about a Hamiltonian which has this kind of a form. This is equal to 3 square by 2m plus some v of x, let's say. Okay, now I have v of x equal to 0 here, but I may have a situation that v of x has this property, v of minus x is equal to 0. Okay, that means it is symmetric. So the symmetric potential. And of course, Hamiltonian depends on x only through this v of x. That means this also has, so a parity operator can be defined. Parity operator on any f of x is equal to f of minus x. Okay. So if v of minus x is v of x, we can say that the Hamiltonian and parity will actually commute with each other. Okay, or in other words, so what is this? Hp is equal to ph. That implies h is equal to ph p inverse. That means it is invariant under parity operation. H does not change. Now, H does not change. The eigenfunctions should be eigenfunctions of both of these operators. That is, you can find eigenfunctions of both of these operators. So that means there are only two eigenfunctions of P. So one eigenfunction is P of f of x is equal to f of minus x. That can be simply f of x. Then this is eigenvalues plus 1. These are called even functions. Or P of f of x is equal to minus of f of x. These are called odd functions. So your eigenfunctions have to be either even or odd. So this much can be said for any system where the potential has this parity symmetry. For example, harmonic oscillator also has this symmetry because the potential is half m omega square x square. So x going to minus x does not change the Hamiltonian.
Yes. So for the second example, a second problem that you showed, so you showed in the transcendental equation part. So the right side, the RSH equation, I couldn't understand how it is corresponding to the circle, sir.
Okay. So so you can see here that
so you said that you have to express eta as a
so eta is alpha a. So eta square is alpha square a square. But what is alpha square? Alpha square is twice m by h bar square into v naught minus e the h square, right? Alpha square a square, correct?
Yes.
But twice m e by h bar square a square is xi square only. So eta square is equal to this minus xi square. So if I take this xi square to the left hand side, I get xi square plus eta square is equal to this quantity.
Yes, so we get an equation of a circle, that is fine, sir. But how is, like, we have to express here in the RHS, it is just minus eta, right? So only that part we have to express as a function.
So
of
minus sign I have taken here. So RHS is just eta, correct?
Yes.
So if you want to plot eta, so what is eta? Eta is equal to square root of twice m v naught a square by h bar square minus xi square. If you plot this, you get a circle. No?
Okay, sir.
Sir, is this method have some limitations as we are not getting an exact value of energy?
You will get exact value of energy depending on the resolution of your plotting thing, right? So even numerically, you will only get an approximate value of energy. Okay, so but you will get an estimate, and you can improve the accuracy as much as you want.
Yes,
Not
sir.
graphically, but numerically. Suppose you are using some Newton-Raphson method to find the solution, then you can improve that accuracy depending on number of iterations and things like that.
Yes, sir. Sir, another question, sir, why we are using only position space wave function in these systems? Can we use also momentum space wave function?
In principle, yes. In principle, you can use momentum space wave function also. But of course, there is you should be able to get some wave function to start with, right? So if
Yes,
you take a momentum space wave function, then you can, if for example, let's say that so let us say that you have something like you have p square by 2m. This is your Hamiltonian, right? So you want to solve h psi is equal to e psi. You want to solve this equation in momentum space. In momentum space. Okay, then what happens in this particular case? Your x operating on any function of d is basically IH cross d by dt of phi f. And p operating on any function of momentum is simply p multiplied by phi f. Correct? So this is what you will have. Okay. Now the question is that when we are stating the problem, okay, for example, when I'm giving you a potential as a function of x, most likely this is what it is, right? A function of x. And then we have to also see boundary conditions. So if the boundary conditions are given in terms of x, that is psi of x equal to 0 is 0, and psi of x equal to a is 0, like this, if you are given in terms of the position, then it is better to use position space. But if your boundary conditions are given in terms of the momentum space, in terms of the momentum wave function, that is when the momentum is this much, your wave function is 0. When the momentum is this much, when then the wave function is 0, or some constant like that it is given, then it makes sense to talk about momentum basis. So it all depends on the given information. How is the problem formulated? So if the problem is formulated in terms of the boundary conditions with respect to value at x, then it is better to use position. It is you can that is to solve the problem. The boundary conditions are very important. Now, depending on the boundary conditions, you should choose your basis. If the boundary conditions are given in terms of the position, then you use position basis. But we can also discuss later that it is also possible by finding the position eigenfunction or position basis wave function. You can convert it into momentum basis wave function, and that is merely by doing what is called a Fourier transform.
Yes, sir. Sir, eigenvalue will remain same, sir. Yes.
When
in this condition, when we use position space wave function.
now what we have done today is only a position basis wave function, correct?
Yes, yes, sir.
Yeah. So the momentum basis wave function can be written as a linear combination of position basis wave functions. Okay? So when
Yes,
you
sir.
write a linear combination, it will be having a linear combination of several different wave functions, right? So
Yes, sir.
yeah. But in this particular case, if you don't have a potential, then energy eigenfunction and momentum eigenfunction are same in some sense.
Yes, sir. Sir, what is the difference between K space and momentum space?
They both are same.
Okay, sir.
K space and momentum space are same. In solid state physics, you talk about reciprocal space. That is also same as the momentum space.
Yes. Thank you, sir.
Yeah.
Sir?
Yeah.
So if we consider particle in a ring, which is a 1D case, but we have degeneracy there. No, because but how can I have degeneracy in a 1D case, sir?
You are saying degeneracy because
particle in a ring, because the LZ commutes to the Hamiltonian.
yes.
So we have degeneracy. But it's a 1D case, like it's a periodic boundary condition and a 1D potential work. So how can have degeneracy in a 1D case, sir?
No, it is something like even a free particle, not on a ring, even if you take a free particle, that also has the same thing, right? Momentum commutes with the Hamiltonian because P and P square by 2m commutes with each other. Okay, so you can have e power ikx and e power minus ikx. These are two wave functions for the particle with the momentum h bar k and minus h bar k.
Yes.
Both of them will have same energy.
So how can we have like degeneracy in a 1D case, sir? Because in 1D case we don't have degeneracy, is the theorem, no?
Yeah, so that is specific to some kind of a. I forgot what is the proof of that theorem, but I think it is related to some application of some boundary conditions. If you don't apply any boundary conditions, you just leave it as a free particle.
Okay.
Then free particle in positive moving in positive direction and free particle moving in the negative direction will have the same energy.
But like if we consider periodic boundary condition, because the particle in a ring, then we also get the degeneracy.
That is also like circular, I mean, clockwise and anti-clockwise.
Yes, sir.
Will have same energy.
Okay, sir.
Sir?
Yeah.
Sir?
Yes,
Sir,
yes.
if we compare the ground state energies of all these three potentials, how we can order them, sir?
Yeah, so maybe you can think about it. Ground state energies, let's say that we have three boxes today discussed. Now, let's say that bound states exist in each of these. So, let's say you have a box like this. where it is infinity both sides. So let's say I call this as E0A, and so let's say the ground state energy for this is E0B, and then ground state for this is E0. Okay. So let's say this is V0, and this is also V0, and this is also V0. Now, if you want, I can also think of adding another potential well, where this is from V0 prime, and this is V0. V0 prime is greater than V0, as you can see. So let us call this as E0. Now the question is that order is ground state energy. Ground state energies in whichever order, maybe in descending order. So which of them will have highest ground state energy, and which of them will have the lowest ground state energy? So I want you to think about this. Maybe I can just leave this as an exercise. So use your quantum thinking to get this. I think there was some question in CSIR paper based on this last year or something. So we should develop a way of thinking about the energies in these potential waves. Okay, so your question is given as homework. Any other question?
Sir, can we talk about... Hello?
Go ahead.
Yeah. Sir, can we talk about a number of bound states?
Can we talk about?
Number of bound states.
Number of bound states. Yeah, so you can talk about that. That is, the number of bound states will depend upon your V0, if you take that particular V0. And you can say that if some V0 is there, then how many number of bound state it will exist. That one can talk about. So one can calculate how many number of bound states exist for a given V0.
So without calculating, is there any way of thinking physically and getting the result?
No, with to find out a number, you have to do calculation. Whether the bound state exists or not, such things you can talk about qualitatively, but to calculate explicitly how many number of bound states are there, you have to do a calculation.
Okay, sir.
Okay, so actually, I want to tell you that there is a book by A.P. French. A.P. French is one of the authors who wrote that MIT, like Berkeley series, they have some MIT series. So he wrote a book on quantum mechanics. So he talks very nicely about this kind of some qualitative, semi-qualitative, and some quantitative ways of finding out energies. Is like the question that Mona Lisa asked: how many number of bound states can be there? How to calculate that one? So all such things you can find in. It's a very, very nice book. You once you start reading it, you will not feel like stop reading. It's a nice book, so I would recommend you to take a look at this one, at least for this part of the discussion about the potential wells. This is a very nice.
Sir?
Yes.
I have a basic doubt. What is the difference between countable infinitive and uncountable infinitive?
The answer is there in your question. Uncountable infinity cannot be counted.
Sir,
Okay.
infinitive means infinitive. How can we define like countable, uncountable?
Yeah. So anyway, I will give you a mathematical definition. So countable set. It is an infinite set, but countable set is the one. Suppose if X is a countable set. Okay. So let's say X is equal to some X1, X2, etc. There are infinitely many things. So X is countable. Yeah, X is countable if we can define uh, a 1-to-1 map. A 1-to-1 map between the natural number set to X. N is set of natural numbers. Since natural number set what? Natural number set is 1, 2, 3, etc. Right? So if you can define a mapping from this map to X, since this is countable, there infinity. Countable means okay. Now I understand your question. Countable means it is not that we are able to count or not. So if you want to say 1, 2, 3, 4, etc., okay, you will get tired and you cannot count. That is not countable. But countable means it is possible to count. Okay. For example, this simply means that I counted 1, I counted 2, I counted 3. Then I know that I have counted everything up to 3. Okay, I have not left anything. Then I count 4, then I have counted everything up to 4. Okay, so that is what is countable, or this is also called denumerable. Denumerable and countable are two words that are used. Now, uncountable means I cannot count at all because this kind of a mapping is not possible. Because if you take set of real numbers, so let's say I say 1, then I say 2, but I cannot say I have counted everything between these two because 1 and 2 in between there are infinitely many. Now I take 1 and 1.1, but in between there are infinitely many. 1, 1.01, again there are infinitely many. So I cannot count at all. So this is what is called uncountable infinity. There are infinity between every two numbers, and so there are depths also infinite and then length also infinite. That is called uncountable infinity.
Okay, sir. Thank you, sir.
So if there is a continuous distribution of numbers, then it's uncountable.
Yes, yes. So there are no questions then.
So actually, I have doubt in yesterday's class. Like, uh,
What is it?
like if you can ask now or can I ask next Tuesday, sir?
Okay, so you can ask next Tuesday. Before that, you can keep thinking about it. Maybe it will be
Yes.
clear.
Yeah, I'll try, sir. Yes.